All right, well, I'll do a little bit of theory, and then I'll do a little bit of Python as well. And I'll also have some work for you to do. And announcements. So I need to post the videos. I don't know what was the last video that I posted, probably the Monday of the week before spring break. So I probably have still at least one video to put up on YouTube. I did post the homework sometime last week. I'm gonna make it due a Monday from now. Technically it's due on Friday, but I'll extend it to Monday. I definitely try to make it short and sweet so that you don't have to suffer too much with this one. I think you suffered a lot with the previous one. So this one is, I think, just 3 problems. And one of them is really just like PL3, it's just plotting. And if the starter code has basically, half of the problem. So I think that one should be okay. Then a strong form to weak form, which is very much the same as the one that I did in class for the 2D, with just one change. And I forgot what was the other problem, besides the project problem. There was another problem. Oh, a force vector and a stiffness matrix, yes. It's technically on. It says it's on. How do I increase the volume of this thing? Let's try and increase the volume. Well, battery is about to die, but can you hear better? No. Technically is on. Let's see. Change the battery. Oh, there we go. Hopefully it's better. Good. All right. Do you catch any of the announcements? Yes. Okay. Just that there's a homework that has been posted. I'll make it due on Monday of next week. There's 3 problems. One of them is just plotting, and it's basically the same as PL4. And the starter code has half of the problem, so hopefully that is not too bad. Then one problem is a theory problem, so strong form to weak form. And for that one, it's just like the heat transfer in 2D with just one extra term. So I hope that will be okay as well. And then there's one problem for a force vector and a stiffness matrix. That one maybe is the difficult one, but it's a theory problem. So you just have to do the integrals analytically. I'll talk more about that one on Wednesday because it relates to the solution, the FE solution for 2D. And that's it. So those are the 3 problems. So hopefully, 1 week should be more than enough to get that done. And then for today, we're just gonna finish with finite elements in 2D. And just because I want to do the quadrilateral, that's the one element that I want to do. Just a brief recap of, again, where we are and how does this relate to the FE solution. So we did a strong form to weak form for the heat transfer problem in 2D. Just as a reminder, the heat transfer problem in 2D looks something like this. So divergence of the flux plus a source temp equals 0, where the flux is usually minus the gradient of the temperature, with boundary conditions either temperature is some known temperature at some part of the boundary, which we call gamma T, so known temperature, or the flux is known. So you know Qn at gamma Q. So flux is known. Those are the two options. And then I can just tell you that if you do the strong form to weak form, you end up with an integral of the conductivity. This typically has a conductivity. It's not just the gradient, it's some conductivity times the gradient. So you end up K gradient of W dotted with the gradient of the temperature over the domain minus integral over the domain of W times S, and then minus the integral over gamma Q. This is the only one that survives from the integration by parts of Qn W equals 0. Find T with T equals T hat on gamma T for all W with W equals 0 on gamma. So that is the weak form for the heat transfer problem. Again, this heat transfer problem, the strong form is divergence of the flux plus source term equals 0. The flux is minus the gradient of the temperature scaled by this conductivity with boundary conditions of two types. You either know the temperature, that's the essential boundary condition, or you know the flux, that's the natural boundary condition. To go from that to the weak form, you multiply by the weight function, you integrate, you do integration by parts, and then you apply the boundary conditions. So at the end, the weak form looks like find the temperature with the temperature equals the known temperature T hat on the gamma T boundary. And then the integrals are like that. So the integral over the domain of the conductivity and then gradient W dotted gradient temperature minus W times the source term minus gradient over only the gamma Q of the flux, the known flux. This is the boundary condition flux. Times the W equals 0 for all W's. And the only condition in the W's is that they should be 0 on the gamma T, on the part of the boundary where we know the temperature. So that's the strong form to weak form. And that's what the FE is going to solve. Then on the other hand, we need the discretization in 2D, which is what we have done in the last two classes. We started with triangles. So we showed that in the same way as for the 1D case, what we wanted to do was to build these shape functions, right? And so for the shape functions, we want some functions that are one at a particular node, but they vanish at the other nodes. So if it's the same triangle, hopefully it looks like the same triangle, then the shape functions are like these little pieces of plane, which are one at a particular node and 0 at the other nodes. And so for triangles, for example, we show that we could actually get these functions in terms of x, y. And then given the shape functions, the interpolations are the same as before. So any function is just going to be the sum of the shape functions times the nodal values. So that's the same idea that we had in 1D applies to 2D. And then if you want gradients, so if you want the gradient of theta, then you will do the gradient of the shape functions times the theta values. The slightly different thing with respect to 1D is that in 1D, we only had derivative with respect to x. So all you needed was df or dn dx. But here we have x and y. So we, instead of thinking just one derivative, we have the gradient, which involves a vector with one of the components being the derivative with respect to x and the other component being the derivative with respect to y. So that's what we did, I guess, on Monday. And then on Wednesday, what I was saying is that this idea of defining functions with respect to x, y is actually very difficult to do for arbitrary shapes. So what I did was I introduced the isoparametric map for triangles. And what we did in that case was that, okay, let's not define the shape functions in x, y, but rather let's find a triangle that is always the same. And so we'll define the shape functions in terms of psi and eta, our new coordinates. And for the triangle, we show actually that these are really, really nice. So this was the first node, the second node, the third node. So we showed that the shape functions in terms of this triangle are just psi, eta, 1 minus psi minus eta. So the shape functions get really nice, but the problem is that now you don't have this, right? You don't have if you want to interpolate some function theta, you cannot interpolate it in terms of x, y. So what you need to do is interpolate both the x and the theta. So what are the x and y components? So x is going to be the sum of the shape functions in terms of psi eta times the x coordinates. Y is again the sum of the shape functions times the y coordinates, and theta is the sum of the shape functions times the nodal values of the theta. The idea is the same as what we did in 1D. So when you define this parent domain psi eta and you define shape functions in terms of psi eta, now you need to interpolate both the geometry and the field. So you need to interpolate x, y, and theta. You also have the Jacobian, which is a matrix that contains the derivative of the x and y with respect to the psi and eta. So this has 4 components. And then we also had the gradient of theta with respect to psi. That one was the gradient, the sum of the gradients of the shape functions with respect to psi times the nodal values. Both of these are derivatives with respect to psi eta, so they are easy to get. And with those, then you can finally get what you need, which is the derivative with respect to x is just the inverse of the Jacobian times that gradient with respect to psi. I'll do a little bit more in a sec, and I'll try to do it in Python as well. But any questions up to this point? This is sort of the summary of what we have done in sort of this section 2 of the course. Again, strong form to weak form for the heat transfer problem, discretization in 2D with triangles, either shape functions in terms of x, y, or shape functions in terms of psi eta. For the homework, all you need to be able to do is shape functions in terms of x, y. So that's the only thing that is required for this homework. But in general, what Abacus does is everything is with the functions in terms of psi eta. All right, so today I just want to close with one last set of examples for this discretization of functions in 2D with the quadrilaterals, which I kind of touched upon on Wednesday before spring break, but I'll go a little bit deeper today. And what we'll do on Wednesday is we'll do the system of equations. So we'll do this on Wednesday. And Friday, when we do it, we'll solve it with Python. So that's Wednesday or Friday. So today I'm just gonna close this off with quadrilaterals. All right. So I already did this. Strong form to weak form. This is what we did last time. I mean, this is exactly the same that I was just going over. Strong form to weak form. For the triangles, you can define the functions in terms of x, y, or you can define the functions in terms of psi eta. And the key thing is going to be this Jacobian. And then this is what I was doing last time, and that's where we stopped. So let's do the quadrilateral. I kind of alluded to it, but let's go in a little bit more detail. For this, the idea is going to be the same. So we have a quadrilateral which has 4 nodes in the XY space, and we want to map it to this psi eta space. That's what we want to do. And that psi eta space is going to go from -1 to 1 in the psi and from -1 to 1 in the eta. I already gave you this formula, but we are actually going to derive it because it's relatively simple to do. So if you recall, what is let me just try to do so in the psi eta space, this is the plane, and then we want, and this goes from -1 to 1 in the psi space, and then -1 to 1 in the eta space. This is our node 1. And so what do we want this function to look like? We want it to be 1 at that node and to go to 0 at all other nodes, right? So we want this to be 1 at this node and then to go to 0 at the other nodes. That's what we want that function to look like. So for that, let me ask you, what is a function of psi that is, this is sort of, it's kind of like a plane. It's not exactly a plane. So what is a function of psi? Let me not use n. What is a function of psi such that if you just ignore the eta part, you can see that this function has to go, when psi goes from -1 to 1, it has to go from 1 to 0. What is a function of psi, only psi, that goes from 1 to 0 as you go from -1 to 1? Any guess? Is the linear the same as the 1D? So same as 1D shape function. So we're gonna construct it in the same way. So all we want to do is psi, psi's are so terrible, but psi -1 over -1 -1, right? So psi -1 over -2. So that is the same as the 1D shape function, it goes from, if psi is -1, it's going to be 1. If psi is +1, it's going to be 0. What is a function of eta such that it also is like that, so that it is 1 when eta is -1, but it's 0 when eta is +1. Exactly, exact same thing, but with eta. So it's like this. And that gives us a way of building the shape function that is gonna be 0 at those two and also at the last node. So out of that, actually, the first shape function of the quadrilateral, which is a function of psi and eta, is just the multiplication of these two. So actually, the first shape function, which is a function of both of them, is just going to be psi -1 over -2 times eta -1 over -2. So this is now a function of both psi and eta, such that it is 1 at -1 -1 and 0 at both this, but clearly it's also 0 here, right? Because at this point, both psi is +1 and eta, sorry, psi, the f of psi is 0 and the g of eta is 0. So it also here is 0. So it really will go down to 0 in all other three nodes. So actually, we have constructed that shape function using the 1D shape functions. Similarly, what is the second shape function of psi eta? I'll try to draw it again. Maybe I'll put it down here. So now we want a function that is 1 here, and it goes to 0 at the other ones. So we want this function. And again, we're going to obtain that based on the 1D shape functions. So in this case, we want for psi, we want the second shape function. So we want something that goes from 0 to 1. So that one is going to be psi -1, so +1, over 1 + 1. So again, that's the 1D shape function for psi that goes from 0 to 1. So this one, when psi equals -1 is 0, when psi equals 1 is 1. So it's basically this function right here. And then for the eta, we still want the same one as before. We want something that goes from 1 to 0 as you go from -1 to +1. So for eta is actually the same as before. So eta -1 over -2. So this is the second shape function. And then I'll give you maybe just 2 minutes to write these other two down. All right, so the third shape function, I'm not gonna draw it, but it should be the same as the, so this one is gonna be the same. So psi plus 1/2, that one is the same because the third shape function in that upper corner will have the same, maybe I'll do it. So now we want this one. So we still want this to go, for psi, we still want it to go up. And then for eta, now we also want the eta to go up. So this is gonna look like eta plus 1/2. And then the last shape function is 1 here and 0 at the other two. So that one should have the negative of the psi. So it should have psi minus 1/-2. So the first shape function of the psi, but it should have the second shape function of the eta. So it should be eta plus 1/2. So those are the 4 shape functions of the quadrilateral. Connect them. So those, for example, we will need to code in Python as, def n1, and then it will take in psi eta, and then it will spit out that function value. Similar to what we needed in 1D, we usually don't need just the functions, but we need the derivatives of the functions. So we will need the gradients. So what is the gradient of psi 1? That one is a vector, right? Where the first one is the derivative of n1 with respect to psi, and the second one is the derivative of n1 with respect to eta. So if you take the derivative with respect to psi, then all you end up with is the minus 1/2. So this one is just minus 1/2 times eta minus 1/-2. That is the gradient with respect to psi. And if you take the gradient with respect to eta, you end up again just with the minus 1/2 times psi minus 1/-2. So that is the gradient of the first shape function. With respect to psi, the gradient of the second shape function with respect to psi is the derivative of this with respect to psi, that's 1/2 eta minus 1/-2. Derivative with respect to eta is minus 1/2 psi plus 1/2. Put them here. So typically we need to code all of this. Gradient of the third shape function. Again, this is just gonna be derivative with respect to psi. So that is gonna be 1/2 eta plus 1/2, 1/2 psi plus 1/2. And the gradient of the fourth shape function with respect to psi is going to be minus 1/2 eta plus 1/2, and then 1/2 psi minus 1/-2. Questions about that? Again, I just took derivatives with respect to psi and eta. That's how I got those vectors. All right, so we have the shape functions, we have the derivative of the shape functions with respect to psi eta. Then how do we use this? Let me add one extra page here. And this is where I want to use a little bit of the Python. So let's say we have some quadrilateral in the XY space. This is node 1, 2, 3, 4. Let's say that this has coordinates, I don't know, 0, 1. This has coordinates 2, 0.5. This has coordinates 3, 0.75. And this has coordinates, I don't know, 2.5, 2. Just making it up. So those are the coordinates. For notation, typically I would just use, I don't really divide it into X and Y. I'll just write it as an X with a vector. So we have the quadrilateral with XY coordinates for every node. And then typically we have some field that we want to interpolate, for example, the theta. So we have theta 1 equals, let's say, 2, theta 2 equals 3, theta 3 equals 3, and then theta 4 equals 3. Let's just make them all. That's kind of boring. Okay, let's do 4. So if we want to evaluate theta at some point inside of the triangle, actually the quadrilateral, what we need to do is we need to think of our psi eta quadrilateral. And then same as for the triangle, we have two things that we can evaluate for any point here. And by the way, here they are 1, 2, 3, 4. So for some point here, we need to evaluate both the X so that's the geometry map. So what this will tell us is that for this point here, it will tell us the XY coordinates of that point. It will be somewhere here. And then we can also evaluate the theta at that point. So evaluate the isoperimetric map and the function. As usual, we will also have to evaluate the Jacobian. So again, this one is just the derivative. Well, this is a matrix because it's the derivative of the map. So it's the derivative of X with respect to psi. But these both are vectors. So this is why this ends up being a matrix. And this just has all components. I'll code all of this in a sec. So this one is just the sum of the derivative, the partials with respect to eta. times the xi partials with respect to eta of the yi partials with respect to eta of the xi partials with respect to eta the yi. And yeah, this is the just this one. You just have to check your notes to see the arrangement. And so that's the Jacobian, and then the gradient of the theta with respect to psi. That one is just the sum of the. This one is just the sum of the derivatives with respect to psi of theta and the derivatives with respect to eta. Both of these are derivatives with respect to psi. These are derivatives with respect to psi. So if you want to take gradients with respect to x of any function, for example, theta or any other function, all you have to do is multiply by the inverse of the Jacobian. It also works for the shape function. So if you want the derivative of the shape functions are functions of psi eta, but if you want to take the derivatives with respect to xy, all you have to do is inverse multiply by the derivative with respect to psi. So this inverse Jacobian is what allows you to go between derivatives with respect to psi and derivatives with respect to x. And this is just because of chain rule. Questions? All right. The last thing that I'll say is the integral, because it's the same thing that was for triangles. So if you want to do, it's the same thing as before, same thing as before. Yeah, this I had for the, so you can see that this is what I wrote on Wednesday of last time, and it looks exactly the same. So it really is the same idea for triangles, for quadrilaterals. If you have any other shape, as long as you have the shape functions and the derivatives with respect to psi eta, then you know the Jacobian, the inverse of the Jacobian, using the inverse of the Jacobian to go from the gradients with respect to psi to gradients with respect to x, all of that looks the same. So really the only thing that changes is what do the shape functions look like. Really the only thing that changes is this. If you go from triangles to quadrilaterals, that's the only change. The rest, everything that I wrote here, all of this is exactly the same if you look at it for the triangles or the quadrilaterals. The only difference is that For the triangles, there's only 3 shape functions. For the quadrilaterals, there's 4, and they obviously are different. But the structure is the same. And for the integrals, it's also the same. So if you want to do integrals, it's going to be the same. We have an integral over the element of some function, dx dy, and we don't want to do that integral. What we want to do is we want to transform that integral into an integral over the psi eta space. So the same idea from 1D is we want to go to the nice quadrilateral. So we're gonna end up with d psi d eta. And what we need here is the determinant of the Jacobian. In 1D, we only needed the Jacobian because it was just a number, but in 2D, we need the determinant of the Jacobian. Again, this is true for triangles or for quadrilaterals. And this is the same function f. So this is just a change of variables for the integral. And then at the end of the day, how do we evaluate that? How do we approximate that? What we're gonna do is we're gonna sum the value of the weight of the integration point from table times the value of the function evaluated at that integration point, the determinant of the Jacobian at that integration point, and that's it. And this is the integration point from table. Obviously, now the integration point has 2 coordinates. So the idea is similar, very similar to 1D. What are the integration points for the quadrilateral? They're actually very similar to what you have done in 1D. So for the quadrilateral, the integration points are these 4 points right here. Each of them has weight 1. So the integration points are, this point right here is the same as before. In 1D, I forgot what it is. This is minus 0.577 minus 0.577. That's the first integration point. The weight is 1. Then the second integration point is plus 0.577 minus 0.577. It also has weight 1. Then this one is plus plus. And the last one is minus plus. This is the 2-point Gauss rule. So this is 2 by 2 Gauss. So you can see that the way we get these integration points is just by using the Gauss points that we had for 1D. So in 1D, we only had 2 points. It was minus 0.577 and plus 0.577 with weight 1. In 2D, we have all combinations. So we have 4 points because it's 2 by 2. Obviously, if you had only 1 point, then the best point, and this is what reduced integration. So this will be full integration in Abacus, will be these 4 points. Reduced integration in Abacus for the quadrilateral will be just the center. So this is a 2 by 2 Gauss. So 1 Gauss, then that's just 0,0, weight 4. This is what Abacus calls reduced integration. So that's what Abacus calls full integration for the linear. That's what Abacus calls reduced integration for the linear. If it's a quadratic element, then full integration would be the 3 by 3, and the reduced integration will be the 2 by 2. So it depends on what the level of your element is. So this is for linear. So I think that's it. Any questions? Otherwise, we'll wrap it up here, and then I'll see you on Wednesday. We'll do the solution, the FE solution on Wednesday.